Hi, it's Miss Molesbury here. We're going to continue with chapter 11, and we are entering the part of the unit where we talk about logarithms and what a logarithmic function is. We're covering it in this unit because it is the inverse of an exponential function. So it's tying into our last unit, like our chapter 10 unit, when we talked about inverses. So we're going to rely on some of that knowledge today. Okay, so let's talk about it. A common log is used when we have a base of 10. So we're still going to have bases when talking about logs, just like a base of an exponential function, because they are related. So a common log is an understood base of 10, which is written as a little subscript between the log and the x. But it's common knowledge that for a common log, we don't have to write the base. So the common log, if you just see log of x, it is an implied base of 10. So get used to seeing common log, the base is 10. And again, we'll talk about where this base comes from in just a minute. With a natural log, it is a log with a base of e, which is Euler's number that we talked about last class. And instead of that, we usually write it as ln of x, and it's the natural log. These two have buttons in the calculator that are specially designed when we take the common log of a value or the natural log of a value. So I'm going to point them out in my calculator. They are on the left side right next to the 4 and the 7. So we'll come back and use that later in this video. If you want to get a different base on your calculator, and again, we'll get into this more throughout the unit, but say that we want to type log base 3 of 9, then there's another calculator step that is alpha, window, and number 5. So I can go to my calculator. Green button is alpha, windows on the top row. Go to option 5. It says log base, and you get to put whatever base you want. So I put the little base subscript of 3. I put the 9 in parentheses, and I press enter and get 2. And we'll talk about why we get 2 in just a second. Okay, so let's start by talking about the graph. On the graph below, I've provided 2 to the x power. So think about when we were graphing last class, we said the values that are easiest to use for x's are -1, 0, and 1, because when I plug in the -1 power, it creates the reciprocal. When I plug in 2 to the 0 power, I'm going to get 1, and 2 to the first power is going to give me 2. Those points are plotted for us. We said the domain of all exponential functions is -infinity to +infinity, and the range of the parent function is above 0. Its intercept, it has a y-intercept of 0, 1, and make a note, it has a horizontal asymptote of y equals 0. So now, using our knowledge of inverses, if we were going to find the inverse of f of x, its equation, if I just switched the x and the y here, I'd be kind of stuck. I wouldn't know what to do, and that's why we need logarithms. It's going to help us find an unknown exponent. So I would write this as the log with the same base from the exponential. The base would be 2, log base 2 of x. And I can take this original table and switch all the x's and y's. So it's going to be 1/2, -1, 1, 0, 2, 1. Also, remember the domain and range, since we're switching all the x's and y's, they're going to be switched. So the range will be -infinity to +infinity. The domain will be 0 to infinity, and we'll sketch it in a second. the intercept will switch and be 1, 0, so we're provided an x-intercept on a log graph, and we'll have a vertical asymptote instead of a horizontal one. So I'm going to go ahead and put my boundary, my vertical asymptote, and then I'm going to plot these 3 points. So 1, 0, over a half, negative 1, over 2, up 1. Another point we can plot is going to be 8, 3. I'm just telling you. Also, we could have, remember, the original graph had the point 3, 8, because 2 to the third is 8. So I could switch that ordered pair. And as we learn more about logarithms, that'll be easier for you to understand, like why the log base 2 of 8 is 3. And then I connect them. So the graph never reaches the x-axis, the y-axis, because it has a vertical asymptote of x equals 0. This is the inverse. And then its domain is everything bigger than 0. And I plot those 3 points as well as an additional one, just to get a general idea of the shape of the graph. Okay, so the next part is really going to show us kind of what a logarithm does and how it's related to an exponential function, or to exponents in general. So if we have a logarithmic equation like this, x equals log base b of y, the logarithm itself, we are saying that the logarithm equals x. The argument is what we're taking the log of, so here the argument would be y, and the base would be b. So if we want to rewrite this exponential function here, y equals b to the x, it's going to look like a log, the base is b, just like the base was on this exponential part. The argument's going to be y, and it's going to equal the exponent. So it helps us isolate a missing exponent. And I drew this arrow. This will work every time. If you start with your base and loop around, it'll help you see your base, your argument, and what your equation should equal. Okay, so I'm going to try it again. I'm changing this to a log. The base is 4, and I'm going to make it equal. It frees the exponent, so log base 4 of 16 equals x. The 4 should be a little subscript. The 16 is just the same size as log. This is not saying 4 to the 16th power. This is the argument. It's what we're taking the log of, and it can be in parentheses or without. I'm going to do the one at the bottom that's in the same, it starts as exponential, so start with your base of 3 and loop it around. So it's going to be log with a base of 3 of 81 equals 4. Right? So this would tell me base of 3 needs the 4th power to get to 81. So if I start with a log, I can start with the base and also loop around. So I could do 10 to the 3rd power equals 1,000. Oops, let's not do that backwards. Start with the base, 10 to the 3rd power equals 1,000, and 16 to the 1.25 equals 32. Okay, these should be true statements every time. And one reason that logs exist is just to help you find exponents that you wouldn't be able to find anyway. So, for example, if I say 3 to what power equals 9, you know that x is going to be 2. 3 squared is 9. But if I say 3 to what power is 7, well, it's less than 2. So a log would help us figure that out. It would be log with a base of 3, log base 3 of 7 equals x. And then this would be something that we could type in our calculator to come up with the answer. So if we do finish out this problem, alpha, window at the top, and number 5, 3 of 7, I get 1.771 so on and so forth. So x is approximately 1.77. It's crazy how my brain forgets a 1, I think. So that's just kind of a reason or more explanation of like, what does a log do? Why do we even need them? So it helps us solve for missing exponents. Let's see, at the top, we talked about common logs are a base of 10. So in the calculator, we would just type log x and it knows the base is 10. Natural log is a base of e, and we would just type it as ln of x. So today's just your introduction. We are going to transform them tomorrow along with exponential functions, or next class. But let's go to the back and look at an application. Okay, so this says the Richter scale is used to rate the magnitude of an earthquake or the amount of energy released. An earthquake's magnitude m is determined using the equation m equals the log of I over I naught, right here, where I is the intensity of the earthquake being measured by the amplitude of a seismograph reading taken 100 kilometers from the epicenter of the earthquake, and I naught is the intensity of a standard earthquake of threshold quake whose seismograph amplitude is 10 to the negative 4th centimeters. Okay, so this is a lot of information. Let's decide what's actually important here. Obviously, we have an important equation, and then it does tell us this I is intensity, but not a threshold quake, almost like an initial amount, and it provides it for us. So the intensity is 10 to the negative 4th. So it wants us to write an equation to model the magnitude. So let's make sense of this. It gave us the equation, the log of I over I naught. And I know that I naught, this threshold intensity, is 10 to the negative 4th. So I can go ahead and say the equation we could use is I over 10 to the negative 4th. And notice in this equation, this is a common log because there's no base listed. So the base is 10, or we can just use the log button in our calculator. Okay, so this was write an equation to model the magnitude of a standard earthquake. There we go. Now it says an earthquake in California measured a 6.8 on the Richter scale, while an earthquake in Japan measured 7.2. How many times more intense was the Japanese earthquake? Okay, so we need to compare the intensity. Let's go ahead and start with the California earthquake. So in the equation, here is a magnitude, 6.8, the log of I over 10 to the negative 4th. And if you're like, well, how do I solve for something inside the log? That's why we were practicing rewriting this. So let's rewrite this as exponential. So the base is an understood base of 10. So I'm going to do 10 to the 6.8 power equals, loop it around, I over 10 to the negative 4th. Okay, if I don't want to be dividing by 10 to the negative 4th, I can go multiply by 10 to the negative 4th on both sides. So the intensity Think about exponent rules. When the base is the same, my exponents can add. So this would be 10 to the 2.8 power. And now I have something I can easily type in the calculator. 10 to the 2.8 power is 630.957 is what I'll go ahead and write. 630.957 is the intensity of the California earthquake. Now, one cool trick in the calculator, if you don't know it yet, I need this number later when I compare the two intensities, so you can store it at the bottom left side next to the off button on a normal calculator is STO. So if you press that, you can store your number, the number on the screen as any letter in the calculator. So I'm going to choose to store this as C, alpha C, the draw button here, because that way it helps me remember it's California. That's why I picked C. And now anytime I type a C on the screen, the calculator thinks that it's this nice unrounded number. So I don't have to keep writing the decimal or use a rounded form. Okay, so that was half the problem. That was the intensity in California, and then we also have to go ahead and do the intensity in Japan. So it measured a 7.2. It doesn't seem that much bigger on the Richter scale. So here's my equation. Same steps. I need to rewrite it as exponential. So 10 to the 7.2 equals, and I'm doing 10 again because the understood base is 10. It's going to free the argument of the log. 10 to the negative fourth. And then I'm going to go multiply by 10 to the negative fourth. 10 to the negative fourth. So we have 10 to the 3.2 power. And in the calculator, let's go type that. 10 to the 3.2 power. Ooh, that's a lot bigger. 1584.893. Okay, so even though it didn't seem on the Richter scale to be that much greater, we can see the intensity is actually a lot greater, and to compare them, we really need to take how many times more intense Japan's intensity divided by California's intensity. So I'm going to quickly, in my calculator, while this is still on the screen, press the STO button and store this as J, if I can find J on my calculator. It looks like it's alpha and then the comma, storing it as J for Japan. So if I take Japan's intensity, alpha J, and I divide it by California's intensity, alpha C, hey, it's about 2.5 times as intense. And if you did this with rounded numbers without storing it, you're going to get about the same thing. I just want you to be exposed to it because we use it a lot of times in pre-cal. Okay, about 2.5 times more intense. So, last question here. Let's keep going. I'm going to highlight this. This was technically my final answer here. But number 3, final problem, says early in the century, an earthquake in Indonesia registered 8.3 on the Richter scale. In the same year, another earthquake was recorded in Chile that was 4 times stronger. What was the magnitude of the Chilean earthquake? Okay, so let's see what we're given. We're given, we have a Richter scale of 8.3 in Indonesia. So that's an M magnitude. And it only tells us that in Chile it's 4 times stronger. So not 4 times on the Richter scale, but 4 times the intensity. 4 times I of Indonesia. So let's go ahead and figure out how intense Indonesia's earthquake was. Sounds like it's pretty intense. So 8.3 equals the log of the intensity over 10 to the negative fourth. I have an implied base of 10 here, allowing me to rewrite this. 10 to the 8.3 power equals I over 10 to the negative fourth multiply by 10 to the negative fourth, same steps we've been doing, to get 10 to the 4.3. And let's go type that in the calculator. 10 caret 4.3. Ooh, 19,952.623. I'm going to go ahead and store that as I, like not imaginary I, but it looks like that's alpha x squared. Just help me remember that's Indonesia. So their intensity is 19,952.623. And then it says we need to do 4 times that to figure out, so times 4, right? Or we can just go multiply by 4 in the calculator to get the intensity of the Chilean earthquake. So let's go to the calculator. It's still on my screen. I can multiply by 4. That's a very large number. I'm gonna go write it down. 79,810.493. And then I can go find the magnitude, because that's what it really asked for. The magnitude using this equation. I now know what to plug in for the intensity. So we're going to use the log button in the calculator and plug in this 79,810.493 all over 10 to the negative fourth. I'm going to store this value over here as C. So it's still on my screen. I'm going to store it as C for the Chilean earthquake. And then on the back here, notice M is already by itself. So we just have to go type this with the log button in the calculator and see what we get. So the magnitude is, okay, log next to the 7. Make a fraction. I'm choosing to use my stored value, alpha C. If you want to type it rounded, you're going to get very close to the same answer. 10 to the negative fourth. I'm going to go close the parentheses even though I wouldn't have to, and I get 8.902. So since all of the Richter scale magnitudes have been rounded to the nearest tenth, I'm going to go ahead and say it's about an 8.9 on the Richter scale. So the point of these word problems was just to get you more comfortable transferring back and forth from exponential form to log form, and to show you some of the characteristics of the graph, and then that's what we did earlier, and just to kind of put in your head where we're going with this. So next class, we're going to focus on graphing more and do all of our transformations for both exponential and log functions. Please let me know if you have any questions.